Hi, boys and girls. We are going to now create a distance time graph for Nick's first walk. The first walk that Nick did, and I think that will probably still be in this video, is regular kind of a medium constant speed. Now, for this first one, I'm going to show you how to create your axis. And what you have to do is you have to use a ruler and try to get as close to the line that's on the graph paper as possible. Right. And I'm having a little trouble getting it just perfect, but I'm just going to have to let it go. All right, that was the x-axis, and now I'm getting ready to make the y-axis as close as possible to on the line, and it's still not perfect. We're just going to let that go. All right, I'm going to label my axes. This is my y, and this one's my x, and I love to make them a little fancy when I'm making x and y. Right here at this very corner where the y-axis and the x-axis meet, this is the 0 point. This right here, this point is what you would have on your data table when it says 0 distance and 0 time. That is right here. That means that no time, and we're going to mark the x-axis as our time axis because that's where we're going to graph the numbers for the time that passed. And that also means that no distance has happened at this point. So because Nick started at 0 distance and he started on the 0 meter card, the very first point on our graph is right here. Now, the next thing that we have to do is we have to number our graph. And here's a really important tip if you're making a distance time graph. You are numbering at the places where the vertical and the horizontal line cross each other. So right at the point where the two lines intersect. None of your points will be in the middle of a line on this graph. So you want to make sure that when you number, that you number right on the line. And I have to do it right here. This line represents 1 meter. This line represents 2 meters. And notice that I wrote right on the line, not in the space between, but on the line. 4, 5, 6, 7, 8. And I know that I can stop at 8 because I had 8 meters marked off on the floor in my living room. Correct? All right. Now, the next thing that I'm going to do is I'm going to look at my data table. And for my time, I only went up to 11 seconds. So you can see I made this graph have lots more room than it probably needs, right? So I could just go to 11 and still have lots of room left over. But remember, again, I want to write right on the line. So if you're using graph paper like mine, you have to write really tiny. All right. And I only need to go to 11 seconds, so I'll stop right there. I'm also going to mark my unit time in seconds, and my distance was in meters. I'm just going to put an M for meters because that's actually the correct abbreviation for it. Now, I set up my data table so that the time would be first because the time is represented on the x-axis. And this, actually, for you guys, last week you were working on coordinate grids with Miss Dickerson. And so you probably already know that the x-axis inside of a coordinate is first, and then the y-axis is right beside it. So in order to make my coordinates from this data table, right, then I just go from left to right. So my first coordinate is 0, 0, which I've already graphed right here because we moved over none and we went up none. My second coordinates is just 2 and 1 because it was 2 seconds. So see, I'm going to come over to the 2, and it was only 1 meter. So I'm going to make my second coordinate point right there because it was 2 seconds that passed and only 1 meter had been traveled. Make sense? My third coordinate is 3, 2, and I'm going to go over to the 3 second because the second is the first one. And when you graph, you always do X first. Now, I always do this. I say that you've got to crawl before you can climb, like a baby crawls first and then climbs up. But probably Miss Dickerson told you something even cuter to help you remember which way to graph. But either way, I'm going to make a little line to let you know that for the first number, you're going over, and for the second number, you're going up, right? All right, so the next chord, oh, so this is 3, 2, so we're going to go over 3 and up 2. All right, and then for my next one, my seconds was 5, and my distance was 3. So I'm going to go over to the 5th second, and I'm going to go up to 3. All right, next I'm going to do 6, 4, and I'm going to go over to the 6th second and up to the 4th meter. The next one is 7, 5. I'm going to go over to the 7th second and up to the 5th meter. All right, next is 8 and 6. I'm going to go over to the 8th second and up to the 6th meter. All right, and I'm going to go over to the 10th second, and go up to the 7th meter. And last, I'm going to go on the 11th second to the 8th meter. Now, what you see is a line that is what kind of line? Do you know what that kind of line is called? All right, let me go ahead and tell you to be sure that over here, the x-axis is a horizontal line. Now, we won't put that on our graph, but this kind of line is horizontal. And this kind of line is a diagonal. Now, when you see a diagonal form, then that lets you know that your speed is staying pretty constant. Now, Nick's instructions were to walk at a constant speed, but that's hard to do. And if I connect these, right, then you can see that I'm not making a perfect diagonal because whether Nick didn't stay the same speed or whether I captured the time incorrectly, we didn't get to make a perfect diagonal. But right here, look, we did. You see Nick stayed really constant and I captured the data beautifully right there. So we have a section where we got a good solid constant place. Because diagonals mean your speed stays the same, and a speed staying the same is called constant. Like if mom's ever telling you you're constantly talking, right? That means you're always talking, you never stop, you're always staying the same, you're always constantly doing it. A constant speed is no acceleration, no change in distance, no change in direction, and no change in speed, just the same speed constantly. For instance, in Newton's first law, an object in motion stays in motion. It'd be like traveling in space, a constant speed, never stopping until a force is applied, and that would look like a diagonal. All right. If I finished connecting my lines on my line graph, you can see that we had a little bit of discrepancy, whether Nick was walking a little too slow or I was a little too slow. But you can see overall, I have basically, all right here, I have basically diagonal, and diagonal equals constant speed. Constant speed. Now, the place where we got a true representation of this is right here. We got a really perfect diagonal going on in that section. So I can show you. And the thing is you notice like this axis is a 90-degree angle. And do you see how the speed is kind of right in the middle going up? That's kind of a 45-degree angle. If I did it really straight, it's almost the way we did it, pretty much a perfect 45. which is a nice medium speed represented on a distance time graph. So basically, this is just a medium constant that Nick walked, and we did a pretty good job of maintaining a medium pace with also me collecting the data fairly accurately. All right, so the main thing to know from this first walk is this: diagonal is constant speed. And if your diagonal is just like this, then you're probably going a medium speed, sorry. Right? If it's not too steep, here we are. If it's not too steep or too flat, then you're pretty much going a medium speed. Constant. Okay, oh, I spelled it wrong. Okay, now I knew why it was looking weird. Constant speed. There we go. That's right. Basically diagonal, constant speed. All right, y'all. Thank you for your time.